Okay. You remember last session we started with DC switching mode DC power supply, and we discussed the flyback. Flyback is a converter just improved, occurred in the book boost converter where we add high frequency transformer. Another converter could be classified as part of switch mode DC power supplies, unidirectional core excitation, is the forward converter, which is basically coming from book converter or step down converter. As you can see here, this is my supply, and this is my load, my output, which is RO here, RO here. And here we have the capacitor, the inductance as a filter, low pass filter. We have two diodes, diode here and diode here. We will talk about how they work. Primary with N-turn ratio, secondary with N-turn ratio. Rather than, we have a switch alone, we will put here transformer, high frequency to make the isolation required for the switch mode DC power supply. Now this circuit, this transformer could be used with 3 windings, 2 on the primary and 1 on the secondary. As you can see here, on the primary we have N1 and N3, on the secondary N2. Now the same details regarding D1, D2 are inductance, capacitance, input, output, but just we put here diode, another diode D3, opposite direction. I will explain how the circuit works, but let me go to the equivalent circuit of this transformer. As you know, for the primary, we need to add magnetizing inductance. Okay. Now have a look. When a switch is on, it means between 0 and V on, the full voltage appear across the primary. As you can see here, this voltage appear across the primary. Current will follow here. This switch is on. Okay. Current will follow here back to the supply. The same thing. Current will follow here back to the supply. So this solid point will be plus. Another plus here, okay, and another plus here, okay. Now for this plus on N number 3, it means the diode D3 will be open circuit, will not conduct. You may say, why from the beginning we have inductance on the, let me say the primary, another inductance. I will talk about it, but let me finish this one. And the diode here, D1, will conduct. So it will conduct, this one will be open circuit because it's reverse bias, and current will follow through the supply, from the output, the load, back to the winding. Voltage here, as you can see here, V1, the voltage across the primary is this voltage, which is VD. When the switch is off, let me just clean the board, 1 second. Yes? Yes, Khalifa. Recording. I'm recording. By the way, I'm recording and uploading. It is there. You will find it in the MS SULMS. I will put it there. Plus, I will put it in. It's there already downloaded after I finish in the Microsoft team. But before I start the week, I already have a pre-record uploaded. So before you come to the lecture, you can listen to the lecture before you come. Okay. Now I'm recording. Next, when the switch is open circuit, as you can see here, when the switch is open circuit, energy stored in magnetizing inductor needs to be released, demagnetized. So it will follow in this direction. So plus here, minus. So the solid will be minus, the solid will be minus, the solid will be minus. For minus here, it means diode D3 will conduct. And if it is conduct, it will return back the energy. It's releasing. So we save energy here. Yeah, that's right. We are saving energy here. Okay, great. Now, this is one. The second issue is when negative here, this diode will be open circuit. So the energy stored in inductance here will be released through the diode D2. So as you can see here, the voltage across V1 now is this voltage appear here, transferred to the primary. So it will be N1 to N3 VD in the opposite direction, definitely. So as you can see here, this is the voltage. Okay. What about the current? For the switch, when it's conduct the current, the next inductance current. The current here, if you assume that the circuit is ideal, then the same current in the inductance. And when the switch is off, the current will be 0, as you can see here. For I1 current in winding one here, it's lower than definitely because it's magnetizing inductance, and part of it in the magnetizing inductance here, and part of it in this one. When it is open circuits, it's reverse its direction, and as you can see here, in the opposite direction and release. Now, definitely the primary winding times current equal secondary winding times current. Now, this is in the situation of on, as I mentioned, this is the same graph. I just copy pasted it again to explain on it. When the switch is on, the voltage of the inductance, okay, equal to the input voltage minus output voltage. Whom say this? Kirchhoff. And when it is open circuit, you see here, I mean, I'm talking about, let me change the color. The voltage here equal to this voltage plus this voltage. So inductance voltage is input times minus output. When the switch is open circuit, now this part already separated. We have inductance, capacitor, and resistance in parallel. So the voltage will be minus VO output because they are in parallel in the opposite direction. Now, if I equate these and rearrange, I will get the relationship for this forward converter. Oh, V output over V input equal D. Yes, it's equal D. This is book converter. Yeah, this is what we are saying. It's book converter. It is step down converter. Just we added here the turn ratio. Turn ratio became part of the the formula. When the switch is off, I1, it means in the winding here, in the winding, equal minus IM. You see here, current here in this direction equal current here. So they are opposite. Okay, this is I1 in this winding, and I magnetizing in this winding. Okay. And I3, the current in the diode, we mentioned that diode 3, it will be forward bias, and it will conduct the current back to the supply. So it will be N1 to N3 times I, transfer from winding to winding. What about V1? As I mentioned, V1 will be minus N1 to N3 VD, as I explained in the figure here. It came from where? It came from here. The current will follow here, so it's a transfer to primary. Okay, because the primary circuit is open circuit now. Now, to find the constraint for the duty cycle, as you know, duty cycle, theoretically speaking, hypothetically, from 0 to 1. Now, as much as the range is wider, as much as the controller is better. It means if I have that duty cycle between 0.2 to 0.8, it's better than to have it from 0.4 to 0.6, because the range here is narrow. The range here is wider. This means I can control in the first one better than the second one. The second one is limited. Now, to find the maximum, because why they find the maximum duty cycle? Usually they want to see the constraints. Now you are adding here in this circuit high frequency transformer, and you know that the high frequency transformer have the problem of saturation. You study this in transformer, in energy utilization and conversion. Okay, so this creates a problem. So we want to see this, how much this will affect the duty cycle of my circuit. I want to know the constraint. It's, you know, they found that the relationship between T magnetizing time for the transformer to be magnetized with respect to the total time is the ratio of the primary, okay, N3 to N1 times D. And this will reach the maximum when this part, Tm over Ts, they found it to be when it is equal to 1 minus D. So when we rewrite this equation here, we can find the D maximum, the maximum duty cycle. This will show me the constraint, which is 1 over 1 plus N3 over N1. Now, N3 over N1, the worst situation is that we have 1 to 1. Okay, when it's a 1 to 1, it means there it will be 1. 1 plus 1, 2. 1 over 2, it means 0.5. Oh, this tells me that the constraint for duty cycle is 0.5. So this circuit have a constraint. Similar to what we discussed already in flyback converter, we mentioned that we can connect them in series or parallel, either two switches in this way. This one, the same circuit, just discussed. But we put here two switches in series. Do you remember why we put them in series? What is the reason? They on together, they off together. Anybody remember? Okay, let me remind you. Rather than we have one switch handle the full voltage, we will have two switch, each one handle half of the voltage. So to reduce the rating of the switch, voltage rating of the switch, blocking. And we can connect them in parallel, as you can see here, one circuit, another circuit in parallel connected here. This because we want to increase the reliability of the circuit. Now, after we finish the unidirectional core excitation, which is flyback converter, forward converter, let's go for the bidirectional. Bidirectional, it's an inverter. Let me start with push-pull. You remember push-pull? Push-pull, we have here two switches. Definitely, these are freewheeling diodes. And we have transformer with center tap at the primary. Just to remind you, we discussed this. When the switch 1 is conduct, current will follow here back to the supply. When the switch 2 conduct, current will follow here back to the supply. Okay. Now here we put rectifier. Okay. Let me explain how the rectifier work. When pulse is positive, here positive, definitely this switch D2 will be reverse bias. It will not conduct, but D1 will conduct the current. You see here. Back to the supply. Okay. When negative signal came, okay, this diode D1 will be reverse bias and D2 will conduct. So the current will follow here. As you can see, back to the supply. Okay. So we have at the end full wave rectifier with two diodes, but because of the center tab here. Okay. Now, let me erase so I can clean the board. 1 second. Okay. Okay, it's already cleaned. Okay. Now, let me show you when the two switches are conducting at the same time. Okay. Or let me say, this is another the other circuit when we get it improved. But let me talk about here when the inductance here release its energy. When it's release its energy, they are off both switches. What will happen? This energy will release in this way and will reach this point. Part of it, half of the current will follow in this direction, half of the current will follow in this direction. Okay, and they join here again and they close the circuit. So the current will be half. Now, if I come to find VOI is the voltage across here, okay, on this line. Then at the beginning, we have VD transfer to the secondary, VD times the turn ratio. When the switch is on, switch 1. When the switch 1 is off, 0, nothing, okay? And then when this energy will be released. And when the switch 2 is on, again, we have the voltage. When it is off, release and so. What about the current? Current for the inductance is clear, increase, decrease, increase, decrease. But let me show you the diode current. Diode current, ID1, I will sketch only D1, ID1, don't need to sketch ID2 because it's similar, but the opposite places, they place their places. ID1 will conduct the same current when the switch is on, switch 1, the same current. When it is off, both off, the current you see reduced to the half. Why to the half? Because as I mentioned, energy here will be released, half of it going in diode 1, half of it going in diode 2. Same discussion applied for push-pull, applied here. The output the inductance voltage is the difference between input and output. And when it is off, you see here, when it is off, this inductance will be in series because they are here short circuit they make. So it will be in series with the capacitor with the resistance. So the voltage will be minus VO. If I equate them, I will get the formula. Okay, this is the formula. Okay, Just simplify, we'll find the formula. Now, here for push-pull, okay, by the way, here too came from the double of the voltage, as I mentioned before in the push-pull converter. Still, the same constraint of duty cycle, the maximum duty cycle will be 0.5 is applied here. Let's change this is the same previous rectifier circuit, but I'm talking about the input here. I change it to one leg. What will happen? The same discussion applied in the previous circuit. The only difference here, you can see that the input voltage is VD over 2, not VD anymore. So if it is VD over 2 in the output, there is no 2 here, as you can see here. This is the formula. Let's go for full bridge, the same previous circuit. Only difference here is VD, not VD over 2. And in the output, similar to push-pull, it will be multiplied by 2. And this tells me that the turn ratio of the half bridge is supposed to be double the turn ratio of full bridge to have the same output. Now, some improvement could occur to the push-pull converter to increase D greater than 0.5. I mean, to cross the constraint. What they did, they put inductance, as you can see at the beginning. You remember the boost converter? When we put on the input inductance, because we want to store it, then when it released with the supply, it will make boost effect. So what they did at the beginning, they switched these two switches together on. So the energy coming from the supply through the inductance to store energy. Part of it here, part of it here. They join again back to the supply. Next, one of these two switches will be conduct, either T1 or T2. The operation is similar to the push-pull we just discussed. Okay. By the way, this circuit, either two switches conduct or one switch conduct. There is no way that the two switches are not conducting. Okay, for this circuit. Now, what will this lead to? This lead to change the formula for the push-pull. It will come in this way, and this means that duty cycle will be greater than 0.5. Sorry. Now, one more issue to be mentioned in the switch mode DC power supply is the transformer, is the high frequency transformer. Okay, you remember the relationship, just to remind you, between H and B, flux density and intensity. The relationship is this way. Okay, this is a quadrant 1, this is a quadrant 3, this is remnant BR, and this is the maximum BM. Okay, and similar to this one, this is typical one from datasheet, taken from datasheet. But I would like to talk here about the core losses with respect to the flux density, because when the flux density increase, what will happen to the core losses? Increase definitely, but the frequency is another player coming here. This, as you can see here, different frequency, 10 kilohertz, 5 kilohertz, 1, and when it is increased, we can see that the here the losses will increase. So these need to be considered. Yes, from one side, you are looking to increase the frequency because the speed, you increase the speed now. Okay, so this is the new technology, the new trend, but at the same time, you need to consider that the losses will increase. Now, core losses density calculated using this formula. Let me read and explain the formula. It is K is a constant. Frequency, switching frequency, rises to power A, another constant. Delta B max is the swing, a peak swing in the flux density. Okay, rises to power B is another constant. Okay, K, A, and B, all of them related to the material, the type of material used for this transformer. Okay, it's taken from the data sheet, as I will explain later on. Now, what about frequency? This is clear from the design. We know that's 10 kilo, 20, 100, whatever it is. Delta B to be calculated by using this formula. What does the formula say? It says that it is equal to input voltage divided by 4 and turn ratio, AC cross-sectional area of the core, and the frequency here. Some constraints need to be considered when we're dealing with delta P max, and you are adding in the circuit a high frequency transformer. you need to consider its effect on the operation, its losses, its saturation, when we lose the control, what is the constraint of a duty cycle. Yes, it is another parameter added to the formula, but at the same time, it's add more pressure on duty cycle. We are not open. I mean, how this will affect. Have a look. 3 points to be mentioned here. The first one, maximum flux density, which allow maximum delta P max. We need to be increased. We need to increase the delta P max. So if we need to increase it, we either reduce NI, N1 or AC. Any one of them, definitely this we try to put it outside the equation. We don't play with it. I mean, we need to increase, keep increasing the frequency if we can, but definitely we have limits. The VD will not change it, but the main part to be controlled here is to control NI and NC, reduce them to increase delta P max. But this will make a limitation, especially when the switching frequency is 100 kilohertz, okay? Then there is limitation that it's limited to the B maximum. Saturation is a problem here, okay? In forward converter, or let me say general in unidirectional core excitation, we have limitation of delta P max. It's limited by the difference between remnant and maximum. This curve, as you remember, okay? This is the remnant and this is the maximum. The difference between them. We can see this in unidirectional. As you can see, the unidirectional, this is unidirectional and this is bidirectional. Unidirectional, when the flux density change, variation in flux density change between 0 to maximum to 0 to maximum. While in unidirectional, because we have negative part, so from maximum in the negative side direction to the minimum, sorry, a maximum, yeah, in the negative direction to the maximum in the positive direction, and again and again. Now, most of the information can be taken from this. I will try to give example in tutorial problem. We will solve it to design next week, inshallah, and try to use this data sheet. How we can pick some information from here to solve these type of circuit. In this way, we completed the switch mode DC power supply. What is left? What is left for us to be discussed? Next 2 weeks, we're supposed to be week number 12 and 13 to complete the syllabus. We have still the applications. We will talk about applications using power electron converter for drive, DC motor, AC motor, different type of DC motor, different type of AC motor, different type of controlling, and how we link what you already studied in level 2 in machine with what we are studying here in power electrons, which is called drive, okay, using power electron to drive electrical machines. And also we'll talk about disturbances occurred in the utility, in the network, in the electrical network. There are many disturbances, you know harmonics, but there are many other differences, the disturbances such as swing, sag, spike, dip in voltage, shut off, and so on. What else? We have also, and what to do power electrons converter to control these. What else? Or sometimes it's to produce some of these phenomena. Also, we will discuss the use of power electron converter to control induction heating and ovens. You know, in industry particularly, there is many applications for induction heaters, and we will talk about them. And at the end of the semester, which is week number 13, at the end, last session, we will talk about the protection of our power electron converter, protection from electrical and from thermal, let me say, thermal problems.